Is this all we're doing?
Nope, there's 2 today. If you can read the schedule.
Can we only do one? I'm mentally drained.
It's Monday, Allie. What is Monday? Birthday?
Oh.
Birthday.
I'm like going through and there's like 10 minutes.
All right. So, topic 9.5 deals with free energy and equilibrium. So we're bringing together what we've been talking about with this delta S and delta G and all of that good stuff. And now we're combining it with equilibrium, which we studied in units 7 and 8. The equation here, we've got a couple equations here. Remember, our K value was our equilibrium constant. It's going to take e to the negative delta G times RT. And that's just simply rearranging this equation that's on your equation sheet. We call this the rat-link equation, because it just looks like rat and link, and that's what we get it to. Okay, so unit 7, we saw that our K values can tell us about our equilibrium position. If K is larger than 1, it shows that the products are favored at equilibrium. If K is less than 1, it shows that our reactants are. If we apply the same idea that gives free energy, then we know that reactions with a negative value for delta G tell us that they're thermodynamically favorable. And that means that the products are favored. Therefore, K values that are greater than 1 indicate thermodynamic favorability. So this is the big takeaway from this, is that K values greater than 1 indicate thermodynamic favorability. Okay, that makes sense. All right. So when we are doing this, we are going to convert between delta G and K. This equation allows us to do that. R then is that gas constant that we learned about when we did the ideal gas law. So R is 8.314 joules per moles Kelvin. Temperature has to be in Kelvin. It has to be in Kelvin for delta G to work and for this unit to cancel out properly. So K then is the equilibrium constant. It is, remember, unitless. We have no units there. When delta G is near 0, K will be near 1. As delta G becomes more negative, K gets bigger because the products will be favored. Okay, that's over here. And if K decreases, the reaction will favor the reactants and therefore become thermodynamically unfavorable. Okay. All right. So we have this reaction. We have, I don't know why that came through like that. I don't know what this is. Oh, that's supposed to be up here. That's why. 1.4 times 10 to the negative 6. That negative 6 should be up there. Did it not print right for you guys, I assume? It's not going to let me. Oh, there we go.
You wish I was dead, I believe.
Okay, there we go. That's fixed now. That was looking really weird there for a minute. Sorry about that. All right, so our equation for this then is that rat-link equation. So we have delta G is going to equal RT. And then that's going to be, oops, I'm sorry, there's a negative in front of here. The natural log of K. So given the equilibrium constant, which is right here, we are at 298. They want us to solve for delta G. So delta G is going to equal negative. R is 8.314 in honor of Pi Day, right? 314. Today's Pi Day. Today is Pi Day. 298. And then we're going to do the natural log of this guy. 1.40 times 10, oops, 10 to the 6th, positive 6. There, a little better. All right, so crunch those numbers in my calculator. I'm going to take the natural log, which is the button next to the 4 if you have a TI calculator, natural log of this value, and multiply it by these. And don't forget that negative sign. That negative sign is important because when you get done crunching the numbers, you're going to end up with negative 35062. And what are my units? Well, we got to go back and kind of look and see what our units are here. Oh, here's the colors. Okay, so what were my units for this guy? My units for that were joules per mole Kelvin. And this was I'm going to do that a little differently. Joules per mole Kelvin. And this is Kelvin. And then this guy is unitless. Okay. So when I go through then and I end up canceling my units here, I'm going to cancel. Let's cancel in black. My kelvins are going to cancel out, and that's going to leave me with units of joules per mole. But typically, delta G is seen in kilojoules per mole. So what would that end up looking like if I converted that to kilojoules per mole?
35.
Yep, 35.062, and that's going to be kilojoules per mole. Easy enough? All right, next one is the we do. Again, we're going to calculate delta G here. So my delta G is going to be equal to negative R, which is 8.314 joules per moles Kelvin times my temperature, which they gave me, 298 Kelvin, times my 5.5 times 10 to the minus 3. Now, let's go back up here and look at this one before I go any further. Look at my K value here. Is this going to be thermodynamically favored or not?
Yes.
Why?
Because it's greater than 1.
It's greater than 1. So when we come out with an answer here that's negative delta G, that meshes with this K value, doesn't it?
What does that mean? Because
if K is greater than 1,
Oh, yes.
then it should be thermodynamically favorable. If delta G is negative, it's thermodynamically favorable. So let's look at this guy down here. Is this number greater or lesser than 1? Less. So we expect our delta G to come out to be positive. Okay, so let's see what happens here. And why is it not turn? Yeah, why would it not? Oh, because of the natural log. We have to do the natural log here. That's why. Okay. So when you do the natural log here, that's what I was missing. I was missing my link in my rat link. I had my rat with a K, not the link. I forgot the link. Why did it come out negative? That's weird.
So it's supposed to be negative or positive?
I would thought it was going to come out to be positive, but I didn't look at my answer key. Negative 8.314 times 298 times the natural log of 5.5 to the negative 3 in my parentheses and hit equals. Oh yeah, it did come out positive. I just wrote it down wrong on my answer key. All right, good. Life is good. Life still makes sense for me. Okay. Woo! Okay, so 1, 2, and this is unit list. So my K's are going to cancel. I don't like that yellow. That doesn't show up well enough. How about green? There we go. My K's cancel. And that's going to leave me with 1, 2, 8, 9, 0.8. What are my units?
Joules per mole.
Joules per mole. Okay. And typically this is given in kilojoules per mole. So 12.8908 kilojoules per mole. Thermodynamically favorable or not?
No.
Because this is a positive value, which we predicted from our K. Okay?
If we wrote it in joules per mole on the test.
As long as your units are right, that's all that matters. Unless they state in kilojoules per mole. Sometimes they will, so read the directions. You guys need to get, and I've noticed this on your last test, you need to get in the habit of always writing down your units. Because if you write a number down and you don't write units with it and it has units and they didn't specify, in moles or in this, that, and the other, if you write down the right number but you don't write down the units, they will mark it wrong. So you went through all that work and you forgot your units, they'll mark it wrong.
No.
Nope. All right. So the next topic that we are going to discuss is coupled reactions. Coupled reactions are one of the ways that you can get certain reactions to run when ordinarily they wouldn't. So when a reaction,
Why do you always click on that?
because
Yeah.
my pens don't come up until I do.
Oh, I thought you were looking at other people's comments. Now I was confused.
No, if I hit comments, then they'll let me use my pen.
Ah, I got it.
Before that, these pens don't come up. That's the only way to get these to come up.
Okay.
All right. So when a reaction is thermodynamically unfavorable, so what does my delta G look like if that's the case?
Under 0. Oh, positive.
Less than, my delta G would be positive. What would my K look like?
Maybe it's 3.
K would be less than 1. Okay. So if that is the case, there are two ways, there's a couple ways that you can force that reaction to happen. Okay. One, you can charge the battery. So when you charge your cell phone batteries, that's essentially what you're doing. Okay. is you are forcing that to take on the charge that you need to run your cell phone for the rest of the day. So one way to do that is to use an external source of energy. That's why you plug in your phones to the wall, is to recharge that battery. Essentially, you are forcing that battery to go a direction that it doesn't want to go. The electricity is causing that unfavorable reaction to happen, but you have to have that electricity present. And then you take it off the charger during the day, then it's slowly going through that favorable, so it's positive or negative delta G for the rest of the day when it's off the charger. Okay, so you need that energy to overcome that unfavorable reaction. Photosynthesis, your light, is what is going to happen there. So the light that it needs to provide that, to convert the carbon dioxide and water into glucose, your light energy is able to do that. Again, sometimes you use electrical energy. There is another way that you can make this happen, and that is to drive a thermodynamically unfavorable reaction with one that is favorable. And they call that coupling, because you're taking two reactions and bringing them together. So the negative delta G from the thermodynamically favorable reaction provides the energy needed by the unfavorable reaction. So the delta G of the favorable one has to be larger and opposite in sign than the unfavorable one. So this has to be bigger, but opposite in sign. So it's actually less because it's a negative, right? Okay. So this number here has to be larger than this one, the absolute value of it. That makes sense?
It's not.
This number here that's negative is bigger than this number if you look at
absolute
absolute value.
So you just add them, it just has to be negative at the end.
Yep. Okay. So you add them together and it has to be negative at the end because a negative delta G is thermodynamically favorable. Okay. That makes sense?
I guess you could say it does.
All right. So here
It's negative 30.
they want us to write the overall reaction. So what is, do I have any intermediates here?
Yes, A2.
Yeah.
A2, okay. So that's an intermediate. And then if I write my overall reaction here, that's going to be A2B3 plus C yields 3B plus A2C. Make sure that it's balanced still. Make sure if you do this and it's not, then you're going to have to go back up and multiply these by something. Okay? But this one is balanced. What's my overall amount for this?
Negative 30.
Try again.
30.
Positive 30.
I thought you said it has to be negative at the end.
And what are they saying? Would the reaction below be a good example of a coupled reaction?
No.
No, it's not. It's not thermodynamically favorable, so it would not be a good reaction to have.
Yes.
All right, here is a reaction for extracting silver from silver ore. Is this reaction thermodynamically favorable?
No.
No, because it has a positive delta G. All right. If the reaction were coupled with this guy, would it be favorable? Show the overall reaction and delta G to support your answer.
Yes, because G2,
Okay. So if I have my 2AG2 here, and that is 21.9. And I bring this guy down here. Can you notice a problem as I go to write this? What do I need to do?
Flip it.
Multiply it by 2, right? So I'm going to go ahead and do that as I write it down so that I don't have to go back and erase. And then what does that make me do to this value? Double it. Yep, I need to multiply it by 2. So negative 252.7. Okay. And my oxygens will then cancel out. That's going to leave me an overall reaction of 2Ag2O plus 2C yields 4Ag plus 2CO. And my overall reaction here, then the amount would end up being, oops, I wrote this down wrong. Hold on. I wrote the answer down. Got ahead of myself. This was negative 274.6. And then your delta G here would end up being, your overall would be a negative 252.7. That's kilojoules. Favorable or not?
Yes.
Yes. In the coupled form, it's going to be favorable. Easy enough?
Mhm.
Yeah. After you've come through Unit 8, Unit 9 is like,
This is a
This is-
breath of fresh air.
Yeah.
I'm feeling
Yeah.
a lot better about my
Like
knowledge.
children.
I'm really afraid to take the FRQ, Flippy, of the last test.
I would just take the test.
She knows. She said you should be afraid.
I'd just like you to take it.
You're
All right.
If you fail, everybody can laugh.
Tomorrow, we are going to start in and we're going to learn how batteries work. So that's what's coming up tomorrow, is how batteries work.
Batteries.
Yep.
Batteries. Batteries.